atomic physics. In this chapter, we mainly talk about the models of the hydrogen atom. So, for the model of the atom, right, we need to go back to Dalton, okay, and then later on it's going to be by the Thomson and the Rutherford, and then by Niels Bohr. So this will be the beginning of the quantum mechanics, and then later on it's will be the cloud model. But in this course, we talk about the model by the Niels Bohr. So Bohr's model of the hydrogen atom. Niels Bohr, he tried to develop models of the hydrogen atom. Okay, so he's gonna combine the quantized energy of Max Planck and the idea of the photons by the Albert Einstein and the planetary model of the Ernest Rutherford, and then the Broglie wavelength, and then finally from the Newtonian mechanics. Okay, so we need lots of the knowledge to understand this model. Okay, the model look like this. We know that hydrogen atom consists of one proton as the nucleus and one electron. Okay, so the proton is at the center here. Okay, so this is with the proton with the charge equal to the positive E as the center of the circle, and we have the electron with the charge equal to the negative E and the mass equal to the ME, right? So the electron, let's assume that the electron is circulating around the proton with the radius equal to the Rn and the speed equal to the Vn. Okay, so I'm gonna describe the sub n here later. Okay, so but assume that the electron moves in the circular orbit around the proton under the influence of the electric force of the attraction, because we have the positive and negative charge here. So it means that these two particles must attract to each other by the Coulomb force. These orbits are very special, where no electromagnetic wave is radiated from the electron. Okay, so when explain about this one, right? We know that, okay, we have been known for a long time that when we have the point charge, okay, we have the point charge, let's say the positive one, the point charge here will the point charge here will just emit the electric field in all direction, as you have seen already, I mean from the midterm, right? But now if the point charge moves to some direction, okay, so it also will radiate the magnetic field circulating along the movement or the motion of the point charge, right? So this will be the magnetic field here. Okay, so now you can see that if the charge is moving, so it will radiate the electromagnetic wave. It means that the charge will lose some energy. Okay, then the problem is, if electron is circulating around the proton, it means that this electron will radiate the electric field and magnetic field as well. Okay, so it means that the electron will lose some energy as moving. Then the radius of the orbit should be decrease and decrease more and decrease more to be something like this. Okay, so now to prevent this, then Niels Bohr assumed that, okay, assume that the electron is in the special orbit. Okay, so there's no electromagnetic wave radiated from the electron. So the state of this electron is just called the stationary state. Okay, so I just want to emphasize this. It's called the stationary state. It means that the radius of the circular motion, it cannot be any radius. Okay, it must be a specific radius that the electron can move without losing the electromagnetic wave here. So then he assumed that the angular momentum of the electron is quantized. Okay, so we have seen this one again, quantized, and is written as this one. Okay, so the angular momentum L equal to, if you remember, equal to the momentum, right, and then times the radius of the circular motion. Okay, So the momentum equal to the m times the v and then times the r. So it said that it is quantized, so it just equal to the n and then times the h bar here. So I'm gonna derive this question later. Okay, so let's use first. So now this h bar, okay, h bar is just equal to the h and then over the 2 pi equal to these two values depending on the unit that we need. Okay, and now this n is going to be the number of the state. Okay, the n just equal to the 1, 2, 3, etc. So it's going to be the number of the stationary states. Okay, it's going to be the number of the stationary state here. So in this case, it means that the angular momentum, right, must be an integer value of the h bar. Okay. Okay. So now we just want to understand why we can get this type of equations. The idea just comes from this sentence. The electron in the special orbit. Okay, the electron in the special orbit. Remember, the special orbit is the orbit that electron doesn't lose the electromagnetic wave, right? The electron in the special orbit behaves as a standing wave. Okay, let's talk about the standing wave first. When we have the standing wave, right? Okay, so let's say that we have the standing wave in a string. Okay, we have the standing wave in a string here. So we have the string here. We can have one loop, right, of the wave. Okay, and we can have the 2 loops of the wave. We can have the 3 loops of the wave, and we can have the 4 loops of the wave. Okay, so now let's consider maybe the 2 loops here and the 4 loops, right? We know that the length of the 2 loops equal to the 1 wavelength. So now we have 4 loops, right? It's going to be equal to the 2 times of the wavelength here. Okay, so let me just ignore this one. Now look at this one. If I just put these 2 ends of the loops, right, of these 2 loops, right, and then attach to each other, so you can see that it's gonna look like here. So this will be the 1 loop, okay, and then this is gonna be the 2 loops. Okay, so then this is called n equal to 1. It means that the length, the circumference of the circle here, we have the length equal to the 1 wavelength. Okay, so let me just emphasize again. So then in this case, it means that the circumference, right, equal to 1 wavelength. Okay, but now in this case, okay, so let's see. If we have the 4 loops, right, so if we just combine these 2 ends together, then we have, okay, 1 loop, 2 loops, 3 loops, and the 4 loops. Okay, so in this case we can get that the circumference equal to the 2 times of the wavelength and etc. for the other. Okay, so in this case it means that the electron in this orbit, the electron in this special orbit, right, it will behave as a standing wave. So for the n equal to the 1, the circumference is equal to 1 wavelength. So in this case, for the n equal to the 2, okay, it's with the secondary it's with the second stationary state, right? Then this electron behave as the standing wave consisting of 4 loops here. Okay, then we can get that the circumference here equal to the 2 times the lambda and etc. for the n equal to the 3 and the 4. Then in the general case, okay, in the general case, we can get that the 2 pi, okay, and then times the Rn, 2 pi times the Rn. So this is the circumference of the circle is equal to the n times lambda, right? The n times lambda n. Okay, let me just say lambda n, because the lambda in each case are different. Okay, the lambda are different. In each n. okay, are different. Okay, then next, because the electron behave as a wave, right? Then we can have the relationship between the wavelength of the electron and the momentum of the electron. Okay, so let's see which one, the introduction, right, to quantum mechanics. Here we said that lambda equal to the h over the p, or we can get that p equal to the h over the lambda here. Okay, so let's use this one. Then here equal to the n, right? Okay, so we have the lambda h equal to over the p. Okay, so times the h, and then over the mass of the electron, right? And then the speed of the electron at the stationary state n. Okay, so now let me just move the MEVN to the left hand side and the 2 pi to the right hand side. So we have that MEVN the Rn, right? It's just equal to the n times the h, and then over the 2 pi, which is equal to the n and then times the h bar, right? Because the h over the 2 pi equal to the h bar. Okay, so now you can see that we got this equation already. Okay, so now for the conclusion, it means that this idea about the quantization of the angular momentum of the electron, right? It just comes from the idea that the electron in the special orbit behave as the standing wave. Okay, then what is energy of the electrons in this special orbit? Okay, what is the energy of the electron in this special orbit? So the idea is, we just want to find the kinetic energy of the electron, we just want to find the potential energy of the electron, and then the total energy of the electron, I mean for the stationary state n. Okay, but then to find the kinetic energy and the potential energy, right, then we need the speed of the electron at the orbit n. Okay, and we need the radius of the circular motion at the orbit n as well. How can we find the v and how can we find the r, right? So let's consider this picture again. So we said that the electron and the proton, right, will attract to each other. So it means that we have the Coulomb force. Okay, we have the Coulomb force of attraction between the proton and the electron. And then this force will behave as the centrifugal force as well, right? Because electron is moving in the circle here. So it means that the force, okay, that's the proton attract the electron, right? The Fe. Okay, so this force, let's say the capital E for the electric. So this force will behave as the centrifugal force. So now in this case, we get that the Fe, okay, equal to, from the equation, just the k q1 q2 over the r square, right? So this will be the k and the e square, because the charge of electron and the proton are the same, and then over the radius for the stationary state n, right? This will be the Rn n square. Okay, equal to, okay, so this one we have as the central force. Then we have the m v square over r. Okay, we have the m v square over r. Good. Now we have this one, and also we have here MEVN the Rn, right, equal to the n times the h bar. Okay, so we have the two equations and we have the two unknown variables. We don't know the Vn and the Rn. Okay, it means that in this case we can just solve the Vn and the Rn in the terms of the constants and the n. So let's just simplify this one first, right? Just simplify this one first. So the Rn just cancel out by 1. Okay, no, wait, let's do this one first. So this one we have that the Rn, right, Rn equal to the n h bar, and then over the me times the Vn. Okay, it is this one. Now this question, right? Okay, so the Rn just cancel out by 1. We have the Ke square over the Rn, right, equal to the Me and then times the Vn square. Okay, so now let's just plug in the Rn into this equation. We have the Ke square and then over the n h bar, right, and over this one, so this will be flipped to here, and then times the Me times the Vn equal to Me times the Vn square. So now you can see that Me just cancel out, right, and 1 Vn just cancel out. So then finally you can have that the Vn, okay, the Vn is just equal to the Ke square and then over the n times the h bar. Okay, so now we have the first question for the speed of the electron in the orbit n, right? So now you can see that the larger the value of the n, okay, so the smaller the speed of the electron. Okay, it means that if electron just go further away from the proton, so the speed of the electron will be smaller. Okay, don't forget that this is the orbital speed, right? This one from this picture is to be the orbital speed of the electron. Okay, let me just take note here. This is to be the orbital speed of the electron at any stationary state n. Okay, next let's find the Rn, right? So we just sub the Vn into this equation. Okay, we just sub the Vn into this equation, so then we can get that the Rn equal to the nh bar and then over the Me times, okay, Vn is Ke square and then times the nh bar. So then finally we get that the Rn is going to be equal to the n square and then times the a naught. Okay, let me explain the a naught later. Okay, so now this a naught here equal to h bar square, right, and then over the Me K and E square. If you plug in the number, okay, of the h bar, of the mass of electron, the Coulomb constant, and the charge of the electron, right, you will get a number equal to 0.529 angstrom. Okay, angstrom. So this quantity is just called Bohr radius. Okay, it's just called the Bohr radius here. Okay, so now for the one who don't get familiar with the angstrom, right? So this value is just called the angstrom. Let me check if I speak correctly or not. Nope, not correct. STROM. Okay, angstrom. Equal to 10 to the negative 10 meter. Okay, this will be the conversions. It is the unit of the length, equal to the 10 to the negative 10 meter. Okay, then okay, so this question is going to be the radius of the circular orbit, right? Circular orbit at any stationary state n. Okay, so now we have the Vn and the Rn in terms of the constant and the n already. So now let's find the kinetic energy. Okay, so let's find the kinetic energy of the electron. Then we have that the kinetic energy of electron at the stationary state n is, okay, so it is the Kn, right, equal to the 1/2 mass of electron, and the Vn square, right, equal to the 1/2 mass of the electron. Okay, so now let's just sub the Vn, right? Vn equal to this value, so we have the K times the E square, and then over the N times the H bar, and then square. Okay, so with this you can get that it's just equal to the me K square e to the 4th. Okay, and then over the 2 times the H bar square, and then finally times the 1 over n square. This is the Kn. Again, I mean for the larger n. Okay, it means that for the larger radius of the orbit, or for the larger n, so the kinetic energy of the electron will be decreased. Next, okay, so let's find the electric potential of the electron at the state n. Okay, then the equation is the un equal to, okay, so from midterm, right, we say that u equal to the k q1 q2 and then over r, right? So in this case it's equal to negative k e square and then over the Rn. Okay, because the charge of the electron and the proton will have the same magnitude, right, equal to the E, so that's why it's with the E square here. But then this negative sign just come from the charge of the electron, okay, because charge of the electron is negative, so this you need to put the negative to equation as well. Okay, next, so let's just plug in the Rn into this equation, equal to minus the k e square and then over the Rn, right? Rn just equal to this one, equal to the n square and then times h bar square. Yep, right, and then times the me k and the e square, so this denominator here, which is going to be equal to minus the me k square e to the 4th over h bar square, okay, and then times the 1 over n square here. Then finally the total mechanical energy of the electron at the state n is, okay, so we have, okay, let's say the En, right, equal to the kinetic energy and then plus the potential energy equal to, okay, so let's see that if you add these two equations, these two terms together, you can see that this factor, right, just the same, okay, this factor just the same, but we have the extra factor for the Kn to be the 1/2 and for the Un to be the -1, right? So if you add these two together, it's just equal to -1/2, okay, and then times the constant here, so then just equal to minus, okay, let me copy this one, and then over the 2 times the h bar square, and that's it. Okay, actually these variables, right, are just constant, so then you can just plug in the number into this and calculate, right? You will get that it's just equal to negative the 13.606 electron volt, and then over the n square. So we have the n square here. Okay, oops, so where's not the block, a box? Yep. Okay, let me change the colors. Okay, and one more thing that you can notice is, okay, so let's compare the Kn, right? The Kn equal to this value, which is positive, right? The Kn here is just equal to the absolute value of the En. Okay, because the absolute value of the En just equal to this one, which is equal to the Kn here, right? So these two just equal to each other. So we have this relationship. Oops. Okay, another one is, okay, so let's compare Un and the En, right? So both of them are negative, and this value are just the same except this factor 2. Okay, so it means that the Un is 2 times larger than the En, right? So we can say that the Un equal to the 2 and then times the En. That's it. Okay, so this gonna be equations that we get, okay, from this idea, okay, especially this one, okay, especially this one. Okay, so look at this energy first, energy diagram first. So now this picture, this out of the picture, it's just called the energy level diagram. Okay, it's just called the energy level diagram here. Let me emphasize this one. Oops. The energy level diagram. Okay, so now for the n equal to the 1, right? For the n equal to the 1, you can see that if we plug in the n equal to the 1 here, I forgot the equal sign. Okay, so now if the n equal to the 1, right? So you just sub n equal to the 1, we can get that the En or the E1 equal to negative of the 13.606, which is equal to this value. Okay, for the n equal to the 1, we just call it as the ground state. Okay, we just call it as the ground state. So now for the ground state, right, it's gonna be the most, okay, it's gonna be the most stable state. Okay, the most stable state. So why the most stable state? Because at the ground state here, the energy is the lowest. Okay, so don't forget that we have the negative of a value, and then the larger this value, so the lower this value, right? So we have the negative of the 13.60. So it means that this energy is, the smallest energy, okay, for the hydrogen atom here. So it's called the ground state. So it's been the most stable state. But now for the n equal to the 2, right? Okay, so if you just sub n equal to the 2 into this equation, then you can just compute the E2 to be this value, negative 3.40. So now for the n equal to 2, it's just called the first excited state. Okay, the first excited state for the n equal to the 2 here. Now for the n equal to the 3, right, just call the second excited state and so on. Okay, so then this going to be the energy level diagram of a hydrogen atom. Okay, and one thing that we can see from this picture is the transition of the electron from one state to another state. Example, okay, if initially the electron is at the state n equal to 2 at this point, okay, if we have energy equal to the negative 3.40 electron volt, right? But now if electron just want to move to n equal to the 1, which have the energy equal to negative 13.60 electron volts. So in this case, it means that electron just move from the higher energy to the lower energy. Okay, then the electron must release the energy equal to this value. Okay, equal to the difference of this energy. Okay, so let me take a note here. We said that. Okay, we said that. If electron move from the high n, which have the higher energy, okay, to the low end, which have the low energy as well. Okay, then the electron must release energy, okay, in a form of the photon. Okay, so electron must release energy in the form of the photon. Okay, move here. But then on the other hand, if electron initially is at the n equal to the 1, right, which has the energy equal to negative 13.606 electron volt, and now if electron just want to move to the n equal to 2, which has the high energy, right, it means that the electron must absorb energy, okay, equal to the difference between these two values, right. Okay, let me take a note here. So if electron just move from the low end, okay, which have the low energy, and then to the high end, which have the high energy, okay, it means that the electron must absorb, right, absorb energy in a form of photon. Okay, so electron must absorb energy in the form of the photon. Okay, so now remember, from the higher end to lower end, electron must release energy. But now from the lower end to the higher end, the electron must absorb energy. Okay, making sense, right? Okay, so now the question is, what is the wavelength? Okay, what is the wavelength of the photon that electron must be absorbed or released? Okay, so we just want to find the wavelength of the photon in these two regions here. So compute, let's find an expression. Okay, find an expressions of photons wavelength. Okay, let's say delta E, right? Delta E equal to, and maybe the E final minus the E initial. Okay, equal to HF, right, equal to the hf. So now this frequency is going to be the frequency of the photon which is released or the absorbed, okay, and then equal to the hc over the lambda, right? So now the lambda here just be the wavelength of the photon emitted or absorbed. Now, okay, let's just plug in the value hc over the lambda, right, equal to, okay, let me just plug in the ef and the I into the equation. We have the E, right, equal to this one. Okay, let me copy it. Okay, this is the value of the E, right? Then we have minus the me k square e to the fourth, right? And then over the 2 times the h bar square, 1 over the nf square. Okay, so the nf here is going to be the number n, right, for the final state. And then again, so we have this minus sign, okay, but if this minus sign, see this one, right, it will be the plus. So we have the plus here, okay, and then again times this value times the same value, and then times the 1 over the ni square. Okay, all just equal to okay, so we can just bring the constant out of these two terms, right? So it just equal to, oops, this one, and then times the 1 over the ni square minus the 1 over the nf square. Okay, so this is what we get. Okay, so now let me just move the hc here to this, okay, and let me just say that we have the h bar, right, equal to the h and then over the 2 pi, right? So then we get that 1 over the wavelength lambda is going to be equal to okay, because the, and let me just sub again, let me just sub the k. So the k is here, the k just equal to the 1 over the 4 pi times the epsilon naught. Okay, let me just sub these two into the equation as well. Then finally we can get that it just equal to the me then times e to the fourth, so this one, right, and then over 8 times the epsilon naught square, and then times h to the 3, okay, and then times the c, and that's it, and then times 1 over the ni square minus the 1 over the nf square, all just equal to, we use the r sub h here, okay, and then multiply with this term. Okay, so it means that the whole term here can be expressed as the r sub h. Okay, so what is the r sub h, right? Let me change the color. The r sub h here, which is equal to this one. Okay, if you plug in the number, right, it's equal to the 1.0973 times 10 to the 7th, okay, m to the negative 1. Don't forget that this is on the left hand side, we have the 1 over the wavelength, right? So unit of the wavelength equal to the meter. Then again, unit of the RH must be the same as unit of the 1 over the wavelength. So we have the 1 over the meter here. Okay, so the RH here is just called the Rydberg constant. Okay, Rydberg constant, and that's it. Okay, so now we have equation that we can use to solve for the wavelength of the spectrum already. Okay, and the last thing that I just want to emphasize. Okay, I just want to change this parenthesis here to be the absolute value. Okay, let me just change this parenthesis to be the absolute value. So it means that we don't need to take into account the sign of this one, right? So this one can be positive or negative, but we just want to take only the positive value. So that's why I just put the absolute value here. Okay. Okay. Now let's go back to this picture again. So you can see that. Okay, so let's look at the emission. Okay, so let's look at the emission spectrum. It means that we have the electron initially at the high end. Okay, and it will emit the photon and then go to the lower end. So now for the first series here, it's just called the Lyman series. It means that we have electrons in the state n equal to 2, equal to 3, 4, 5, 6, and etc. Right? And then it will release the photon and then come back to the n equal to the 1. Okay, just come back to the n equal to the 1 here. So this is called the Lyman series. If you compute the wavelength of this type of the photons, right, you will see that the wavelength of the photon will be in the region of the ultraviolet. Okay, the wavelength of this type of photons is in the region of the ultraviolet. So please remember this one, Lyman series, ultraviolet. Okay, so the next thing is the Bohr series. It means that if we have the electron in the state of the n equal to 3, 4, 5, 6, 7, and etc. Okay, it will release the photon, right, and then go to n equal to 2. Okay, to the n equal to the 2. So this is called the Bohr series. And then the wavelength of the Bohr series here is going to be in the visible light regime. Okay, in the visible light regime. Okay, remember Bohr series, visible light regime. And then the next three is the Paschen series, bracket series, and the Funn series. Electron will move to the n equal to 3, to the 4, and to the 5 respectively. Okay, so now for the Paschen series, bracket series, and the Funn series, we have the wavelength of the photons in the region of the infrared here. Okay, so now remember Lyman UV, Bohr visible light, Paschen bracket, Funn the infrared. Okay. Okay, so this is the spectrum of the Bohr series. Okay, this is the spectrum of the Bohr series. Let me just clean this one first. Here. Okay. And wait. Yeah, I just want some space. Okay, here. This is the spectrum of the Bohr series. Okay, don't forget that the Bohr series is for the visible light, right? It means that we have the electron coming from n equal to the 7, 6, 5, 4, 3, etc. It will go to n equal to the 2 here. Okay. Okay, so this picture is the absorption spectrum. Okay, the absorption spectrum. So you can see that the black line, right? The black line here, it just corresponds to the vanish of the photon at this time of the wavelength. Okay, So this is the absorption spectrum, and here is going to be the emission spectrum corresponding to the emitted photon, right? So okay, here, okay. So now this absorption spectrum, right? This absorption spectrum, it just means that electron just move from the n equal to the 2 to the other state, etc. Okay. But now for the emission spectrum here, correspond to the electron just move from the n equal to 3 and then to the 6, right? And then we go to the n equal to the 2 here. So this is the emission spectrum. Okay, so one more thing that you need to know about this transition is okay, let's say that initially when we have electron which is at the state n equal to 1, right? And let's assume that this electron just jump to n equal to the 5. Like this. Okay, from n equal to the 1 to n equal to 5. We know that electron at the n equal to the 1, right? It's just in the ground state. So here at the n equal to 1, the energy of the electron will be the minimum. So it's going to be the most stable state that electron can have. Okay. But now if we just give the energy to the electron, and if electron just jump to the n equal to the 5, right? So it means that at this state, the electron is unstable. It just want to go back to n equal to the 1 again. Okay, just want to go back to the ground state again. So we have many possibility for the electron to go back. For example, it can just jump from the n equal to the 5 to the n equal to 1 directly. Okay, so it means that in this case, the electron will just release only one photon, and the energy of the photon just equal to the difference between this value and this value, right? Or electron can jump from the n equal to the 5 to n equal to the 2 first, and from the n equal to the 2 to n equal to 1. Okay, so in this case, it means that the electron will release two photons. The first photons, we have the energy which is equal to the difference between these two levels, right? And the second photons, we have the energy equal to the difference between these two values here. And now the third possibility is electron can jump from n equal to the 5 to n equal to 3, and 3 go to here. Okay, all from the n equal to the 3, and 3 to 2, and then 2 to 1. Okay, this is another possibility. Or okay, not done yet. Electron can jump from the n equal to the 5, and now from the 5 to 1, or from 5 to 4, right? Okay, and 4 to 2, 2 to 1. What else? Okay, not enough space. Okay, let me just add a little bit. Oops, okay, sorry. All just okay, so we have 5 to 4 and 4 to 1, or 5 to 4, 4 to 2, 2 to 1. Okay, on the 5 to 4, 4 to 3, okay, and 3 to 1. like this. 5 to 4, 4 to 3, 3 to 2, and then finally 2 to 1. Okay, so that's be the possibility that electron can jump. Okay, but now in this case, okay, if we have look at this one, we have 5 to 4, 4 to 3, 3 to 2, and 2 to 1. It means that we will have, I mean, the 4 photons, right, released from these transitions. Okay, now okay, so let's talk about the hydrogen-like atom. It means that it's going to be an atom, right, consists of many protons, but only have one electron. Okay, so the hydrogen-like atom, it means that we have the atom that has only one electron. For example, we have the ion of the helium, right? So now in this case, you can see that we have the 2 proton. Okay, we have 2 proton here, but we have only one electron. Okay, we have only one electron. It means that the charge of this ion, right, it's just going to be plus E. Okay, so now in this case, for the lithium, right, we have the 3 proton. Okay, we have the 3 proton. So now for the neutral lithium, we should have the 3 proton and the 3 electrons, right? But then if we take the 2 electrons out, okay, so that's why we have only 1 electron in this case. Okay, so this will be the examples of, I mean, the hydrogen-like atom. So we have only 1 electron, but we have many protons, right? So this can be the general symbols. Okay, so for example, let's say that if the Z equal to the 5, right? So we have charge the Z minus 1 equal to the 4 here. Okay, so now this C, right, this C, oops, is called the atomic number, which is equal to the number of the proton, right? And now this A is called mass number. Okay, or nucleon number. It's going to be the number of the protons plus the number of the neutrons. Okay. Okay. Then again, we can just I mean, do the same trick, right? I mean, do the same procedure as we have done from here. Okay, but then we need to change the charge of, I mean, the proton to be the C and then times the E, right? So then again, we can get the radius of the orbit to be this one. So now you can see that we have, I mean, this extra C, right, which is the number of the proton here. Okay, and we have the speed of the electron, we have the energy of the electron, right, this one. So for the hydrogen atom, right, we have only this value over the n square, but now we just multiply with the c square already for the hydrogen-like atom. And this equation, right, for the photon wavelength, we have the c square here times the Rydberg constant. Okay, and then again, let me change this one to be the absolute value. I think we use this one to be the Ni and the Nf, right? Okay, so this will be the example, I mean, just comparisons between the energy level diagram, right, of the hydrogen atom and the helium ion here. Okay, so now for the E1, for the N equal to the 1, right, of the hydrogen atom equal to the negative 13.6 electron volts. But now for the helium, okay, for the helium ion, for the N equal to the 1, right, let's see, we have the C equal to the 2 for the helium here. Okay, so it means that I mean the ground state, we have the energy equal to this value and then times 4, right, which is equal to this one. But now for the n equal to the 2, okay, for the n equal to 2 here equal to the 4, and it's going to cancel out with the 4 here, so we get this value equal to this one, which is the ground state of the hydrogen atom.